we're going to start with another learning rule today. All right, so we'll be starting with what is called as the.
So,
Please go ahead.
uh, so before proceeding further, I have a question.
Please go ahead.
So, yesterday I was working on a kind of a data Excel file. Okay, it has 10 lakh rows,
Okay.
and when I try to open it with Jupyter or Google Colab, then when I read the data through Pandas, okay, then it just showing me 2 lakh rows. And same thing happens with Jupyter also. So I don't know why it's happening. I searched so much, but I didn't find anything. So
Okay.
is this
What was the data set about? But normally, I think 10 lakh row should not be a problem. This is what I think. All right, but the most latest versions of pandas, something maybe something it's something related to that also. I'm not very sure about it, but I
so
don't
your
think 10
voice is
lakh
kind
row.
of breaking.
I don't think the 10 lakh rows is a big thing for the pandas to handle. Okay, so I think it's not a issue with the pandas, but uh, are, are you getting any error or something? No,
No,
right?
I'm not getting any error.
Okay.
Right. I'm just getting a less amount of rows. Like I'm not getting the actual data.
Okay, okay. Normally that will not happen, right? I think we have read much larger than that in the pandas or something. Okay, right. Yeah. Mm, okay, let's explore. You also try to find out, right? Uh, Try to explore that. I'll try to find out whether there is any specific reason behind it. Okay.
Okay.
I'll check and I'll get back if I get a solution. All right. Normally that does not happen. Okay. Normally pandas can handle huge amount of data. This 1 lakh, 10 lakh is not a big number, right? For pandas. Pandas can handle
Right.
much larger than that. Okay. But when it comes to the actual big data, maybe there are some issues pandas cannot handle or something, right? Might arise, but not for this number, which you said. Okay, maybe your version issues or something like that, but that should not happen in both the cases, right? At least one of them, like your system or the collab, should had a solution for that. That's what I expect. But anyway, there are.
I tried it with the collab too,
Okay, okay, all right, all right.
and it was showing like 3 lakh rows, nothing else.
Okay, collab is showing slightly larger than your system, right?
Right.
Okay, okay. So you read the size of the data, or how you check the size of the read data? What was
Actually,
the method used?
yes. Um, it was I tried it with Tableau. Okay, so in Tableau, it is showing me the right amount of data, like it has 10 lakh rows.
Okay,
But when I try to do it with Collab, so normally we take the input, take a file, then we read the data, right?
hmm.
Then we get
Get
the
it.
shape of it.
Okay. So you check the check with only shape, right?
So, and when I try other things,
Okay.
like try to explore more, then it was just showing me half amount of data. So I don't know.
Okay, okay. One option is that you can try to look at every function that you can use. You can go for a describe, right? You can go with the shape, you can go with the size, you can go with length. Everything you
Those
try.
were working
Okay.
fine. They were not showing me any kind of error. It was just showing me less amount.
No, no, no. Everything you tried, and in none of them you are getting the actual amount, actual length.
No.
Okay, okay. maybe the other solution could, no, no, pandas itself is the best. I don't want to suggest to go with other, because uh, anyway, ultimately everything will be done by pandas. Okay, so let's explore. All right, so I'll try to find out this
Oh,
problem I'm seeing for the first time. All right, let me also check. Okay, if something comes into your mind, I'll update you maybe in the upcoming classes or something. All right.
sure, sure.
Okay.
Thank you.
Sure, sure, sure. All right. So it actually gives us a new thought that everybody can explore on the same problem, right? So right, you can try to find out if you have a huge data set, something like 10 lakh rows, are you also getting a problem? And if it's a problem, you try to collect such a data set and try to everyone try to read the size and do some data manipulation over there. And if you find a problem, right, let's try to trace it out and let's try to discuss about the same issue, right, maybe in the upcoming classes. Whenever we get a solution, we'll try to discuss. Meanwhile, if anybody gets a solution, right, you can also, right, put your thoughts over here, we can discuss further. Okay, so with that, uh,
Thank you.
yeah, sure, sure, we'll move to sorry, we'll move to the today's topic, which is called as a decision tree. In the past two sessions, we were basically looking at a particular type of problem. It can be regression, it can be the classification problem, but both of them, the linear regression and the logistic regression, right? They were falling under a particular category of machine learning that is called as parametric learning rules. Okay, now the parametric learning is something which is going to teach the machine to learn in terms of the parameters. Now, if you ask me what are the parameters that the machine has learned when we discuss the linear regression or the logistic regression, is if you remember, right, the model which we built, it actually takes an input x. All right, it we have a machine that's a learning model. It's either guesses the label y in terms of a classification problem, or it used to predict a single value along y-axis whenever it was a continuous variable. Sorry, it's called as the regression problem. All right. Now, if you look at the model that we have defined, it is f theta of x comma theta. So if I ask you then what is a parameter, now you can definitely say that the theta was the parameter. So theta was a parameter of the particular model. It can be a regression classification, doesn't matter. So theta was a parameter. I had various columns along my x value. So we used to predict, or we used to classify by calculating what is called as a y cap, that is equal to a theta naught plus x1 times theta 1 plus x2 times theta 2, and so on, depending upon the number of columns you had, right? We used to do this kind of calculation. So that used to fit a particular type of curve for a linearly separable classes, or if you are if you are doing a linear regression to make an estimation of a one single value along your y-axis, that is a continuous variable, then we were trying to fit a straight line. Okay, in both the cases, right, we basically try to fit in the sense make the machine to learn in terms of the parameter, and the same parameters were used to, right, fit a curve. Basically straight line or multidimensional, this will be a plane. Okay, so that is called as a parametric learn. All right, now the basic advantages of parametric learning is something like they are very simple, right? Again, in case of the linear regression, we have had ultimately derived one straightforward equation that can be simply used, right, without even going for iterations. You don't have to run iterations over there. Simply call that equation once, implement that, which is our normal equation. Just bring it in, right? Put your data x over there, and put your data y over there. There is a particular linear algebraic equation that is coming into picture. Just apply that, and you get your optimized theta directly. You don't even have to repeat that again and again. No iterations are required. Correct? So that simple uh, type of learning is possible if you go for the parametric learning. Whereas slightly modified version of the same thing was used for a classification using what is called as a logistic regression. Output of your linear regression itself was used. Slightly modify that by using a sigmoid function, and you get a 0 to 1 output value coming between 0 to 1, which is a real number. You consider that as a probability, and, right, depending upon a class probability, you can decide whether the input data is belonging to class A or class B. Okay, so binary classification was possible using a very simple technique, right? We called it as, though the name says logistic regression, we are applying that for a classification task. For both these methods, we have understood the mathematics behind that. We have discussed the theory part as well as we implemented from scratch. Okay, right. So that, now I justify that what is a parametric learning and what are the various parameters that we use to teach machine, right, to go for a regression problem or a classification problem. All right, now moving on, there are some of the methods which are called as non-parametric, right? So parameters are fine. Now I'll move to the next technique that we are going to discuss today. That will be the non-parametric. Non-parametric learning. So will that mean there will be no parameters? Yes, such parameters which we have used already will never come, right? They are based on the non-parametric comes into picture because these kind of data learning algorithms or the data modeling algorithms, they are, since they are non-parametric, there has to be some method to teach it, right? Teach the machine to how to do a classification, how to do regression, etc., right? They are called as the data driven models. Data driven models, again, they are still capable of performing the regression if required, or they can still do the classification. So that's the first thing. Then, right, the second feature is that you can feed in very complicated data as well. All right, so I can write they are, oh, okay, I think spelling mistake, let me correct. Okay, so these models which are being used here, right? So which are the non-parametric models are there, right? They are very versatile. They are very versatile. ML techniques, that's the first thing. And they can actually handle, right, complex data. And I can say, and they fit very complex. So it's not a data type complex. No A plus JB R angle theta coming into picture. Complex data refers to, let me try to give a simple representation of what we mean by the complex data. Okay, so just to understand that, let me try to consider this. This is the x and say the x and the y axis. Okay, so I try to fit the curve which can actually separate, which can actually classify the two classes of data points. Let me try to write some points here. All right, maybe like this. And I have another class of data. They lie somewhere here. So if you consider this kind of data points, right, definitely you see the curve, it's not going to be a straight line, that's for sure. Again, this is not going to be a very standard curve which you can give an equation for that. Like if it is a circle, you know, x square plus y square equal to r square. So if it is a parabola, hyperbola, etc., we know that there is an equation for that. But now maybe it's none of them, maybe something like this. So if you try to uh, give or generate an equation for this kind of curve which separates your two classes, then right, which is not a standard, not any of the standard curve. Under such condition, we will be calling those data set as a very complex data, right? So the data, the classes, again, right now I see only two classes. What if you have 4 or 6 or 8 or 10 classes with such classification decision boundaries between them? Then you see this is going to be the complex data. Okay, so complex in the literal meaning is not like 4 plus 6i or something like that, not a complex numbers. Data set is complex, or you can even call it as a complicated. All right, so these are the characteristics of the in general when we say parametric learning, this is what is meant by that. Okay, so parametric non-parametric, sorry, my mistake, I said parametric, I correct. Non-parametric have non-parametric learning models have these kind of characteristics. Now let's move ahead. Let's go straight forward to the decision tree. Now, what are the characteristics of decision trees? Again, they are, since they are non-parametric, directly we will see the data is going to drive uh, the model building procedure, the training procedure. All right, so directly I'll write the data driven. So since it is non-parametric, definitely very complex data can be fit by very easy over here. Okay, so that's the second feature. I'm not going to write that. Now the very peculiar feature of the decision tree is that there is an algorithm, right? So it's called as okay, let me write trained by a specific optimization algorithm that is called CART, C-A-R-T. Right? You might have heard about this, right? Many of you will definitely have come across this at some point. So what is a CART? So that stands for classification, and R for the regression, T for trees. All right. So that means we need to learn what this card is going to do, how the fed data will be used by this card algorithm so that you can build a tree. The name suggests there is a tree, right? So tree structure, maybe you have studied in computer networks or any other algorithm based the subjects which actually deals with the how to build algorithms, how to go with the computer architecture, software architecture, etc. Many part we have seen the trees coming into picture, right? So as we expect, there will be a root. From the root, we the tree starts growing, and as it grows, you may encounter various parts of the trees. Correct? There will be a node. From that node, you may have branches coming up. Branches may end up with the sub branches, and when you have sub branches, you will be definitely failing. At some point, you may reach a point where no further extension possible. You will call it as a leaf possible, right? So uh, all these terms are going to come in our discussion, right? And as the tree, because of the presence of the word tree there, it's obvious we can expect that. Then decision trees. So you will make a decision at every wherever you find branching. Wherever there is a branching happening in a particular node, it means there has to be some decision that takes place. So for the simplest possible is something like yes or yes means you go right, no means you go left. Once again, you encounter a node, take another decision. Now, based on what you will take a decision is our first question that we will be trying to answer. Okay. And the second question is that how can machine learn? This itself is a particular question I should ask. All right. So at a particular node, you will ask a question, right? So asking a question will help you out to get a result out of it. But training should be the other way around, right? So training is something like for a given problem, given set of X values and a Y, which is a label for a classification problem. During the training, machine has to identify, okay, which question I should ask. Correct? Again, there are several orders of the questions. Like I may have 10 different questions to ask to come to a conclusion. All right. But definitely, there it's very interesting to know that how the machine identifies out of those 10 questions which one should be asked first. Okay. First question is yes or no. Again, you yes will take you further, no will also take you further. Yes will further divide into two branches. There you ask one more question. No will also get divided into two more branches. There you ask one more question. So how this ordering of the questions uh, will be formed by the machine, right? So that's what is all about this cart, right? Classification and regression tree. This is a algorithm. All right. So we are going to look at that first. Right. All right. So now uh, let me tell you about uh, the way in which we will approach this whole concept, right? Anyway, our fundamental idea is still same. We are basically going to look at the theory part first. All right, then maybe we'll form a problem and we'll try to solve the problem, right? But before that, there'll be some basic coding, and then we'll take up the actual problem, the actual data set, and we'll try to solve. All right, so this is the basic approach, irrespective of which algorithm we are studying. Okay. But inside the first part, that is looking at the theory aspects of a decision tree, I would like to give a plan of action or our approach. All right. So normally, uh, okay, let me write here itself so that I can save some time. I don't want to tell something and write something again by wasting some time. All right. So let me do something like this. All right. So this is our approach for this particular algorithm. First, we will look at the various commands. All right, so I'll directly give the scikit-learn commands today. Okay, initially I'm going to give that because later on uh, I may not get much time over there. So I don't. I want if at all I want to go faster. I don't want to miss saying this. Okay, so that's why. So first we'll be looking at the commands of decision tree. I can say training. Okay, then I will formulate a problem that actually helps us in visualize a decision tree. Okay, we assume that training has already occurred, and I'll try to formulate a problem. Okay, training is already occurred, we'll assume, and later on at the end, towards the end, we'll come back to the training part as well. Okay, how the training happens, anyway, we will be looking at that in pretty much detail. But before that, this gives you a flow. This is going to give us a flow. All right, then third part is actually going with a prediction. Okay, so prediction with the help of decision tree. So that's why I said we'll initially assume that the training is already done. Okay, so once we know what are the various parameters that machine has to learn in order to make a decision, it becomes easy for us how do we make sure that machine learns those what you call parameters. All right, so that's why our approach is slightly different for this case. All right, then maybe the fourth part we will be discussing about okay, definitely the maths behind, right? And later on, maybe I'll touch what are the advantages, disadvantages, etc. All right. So that's our whole idea behind decision trees. All right. So I'll start with uh, the the first part. That's a commands of decision tree training. Right. So I'll directly write that is uh, sklearn commands. Okay. So so far we were using only sklearn as a as a tool, as a library for modeling the machine learning algorithms, right? So, but that's not the only option. Okay, so anyway, we'll be touching other standard libraries such as PyTorch. We'll also discuss. We'll also handle the data using the TensorFlow and the Keras, etc. Right? Many other efficient libraries are there, but as of now, let's restrict ourselves to only sklearn. Let's get very familiar with everything that sklearn provides, so that other advanced libraries such as PyTorch, TensorFlow, Keras, when we use, right, we'll have some idea, because everything is something like advanced level tools. So sklearn was old and it's also very efficient. I'm not complaining about it. Okay, so to start with, it's better to go with the sklearn itself, learn it completely, so that you know every aspects of a complete library which can handle each and every aspects of machine learning. Okay, but again, everything has a drawback. So later on we'll see that okay, this is not sufficient to handle something like as a deep neural network or convolutional neural networks, which falls under the deep learning case. Then we have to move uh, move on, and we have to start using the TensorFlow, definitely Keras, etc. Okay, all right, so let's stick to the sklearn itself as of now. So now you need to import the data set. All right, so again, the advantages of these open source libraries are that there are several built-in data sets available, right? Because whenever a new learner comes into uh, picture, he should not uh, get stuck saying that I don't have a data set, because sklearn, etc., they are the data handling, right? The data modeling libraries. So normally, right, not only this, even the TensorFlow, even the Keras or PyTorch, etc., will have its own data set available, right? At least to learn something from those data, from those libraries, you can use the data set which is available. All right, so I'm going to start with one such example. All right, so normally, let me try to import. So this is from sklearn dot datasets. Let's say that we bring it because our today's problem will be basically looking at a particular problem. That problem will be defined based on this data set itself. Okay, so from this you import the, I think there's a name. Let me come back to the exact name later. I'm not able to recall that. I think load iris. Okay, this was the, sorry, not irid, it's iris, IRIS. So it's a iris data sets. The name is iris, okay, IRIS, which actually consists of three different classes of the flowers. Okay, the dimensions of three uh, sorry, dimensions of three different classes of flowers. Right, so it's a iris data set, and normally, right, we'll bring the classifier, we'll load the classifier again, that is present inside the sklearn dot, they present under trees. Okay, so TREE, you try to import decision tree classifier. So it's easy to remember, right? The word decision tree classifier itself is the identifier for that particular classifier. Okay, then maybe I'll load iris equal to load iris. Okay, define x, some x you can define. This is iris dot data, and maybe I'll say all the rows and the first column, as I observed, first column is just a number, so second column onwards. Okay, so 2 till the end. This is what you can do. Then the y can also be defined. Okay, so how do you define y? So that is iris dot target. Okay, these are very straightforward. And how do you fit? If you remember, you need to create first you need to instantiate your function. Okay, so that is maybe uh, dt decision tree is equal to decision tree classifier, right? You can actually specify uh, many parameters here, but for this problem which I'm trying to discuss right first, I'll use a parameter. I'm going to talk about this parameter in a while. Okay, so I'll call it, say, max depth. All right, this is equal to 2, right? Just hold on, I'll explain this, all right, in a while. All right, so this is my the instance of this. Then you can simply call dt dot fit your x comma y and proceed. Okay, so that's how, that's a very rough code, right? So it's actually very straightforward, so I gave this part first. All right, and you can actually relate this with our previous works as well, right? So only you change this function, instead of decision we might have called logistic regression, right, linear regression, etc. over there. And the same thing, you get a fit, and you perform the prediction, and depending upon your results you can go with the performance metrics, etc. I hope you are able to remember that. Okay, fine. So let's go ahead now. Let me try to say okay, let me go back and show you what was our next idea. My idea was that, let me assume that there is a pre-trained model. Okay, the model has already been trained. Let me try to visualize that first. Okay, so that means whatever I'm going to draw, I'm going to write now, right? That will be uh, the result of a trained model. Okay, so I'm going to write the result of a trained model now. So again, when we use the when we start writing the code also, I will show you this visualization is possible. Okay, so the one visualization that I'm going to consider right now is something like this. Okay, so let's start with a tree, right? So a tree always starts from a root node. So when I try to visualize a trained tree, this is how it's going to look like. It will say that what particular parameter has been used over here to make a decision. Every node you will make a decision. Okay, that's a fundamental thing everyone has to understand. Again, there will be a question that is going to be asked, and that particular question is based on your data set. So for this case, anyway, I told that we are considering a data set, and that data set, iris data set, it has various aspects of flowers, such as petal length, petal width, sepal length, and sepal width, right? So you see there are four different parameters. So your X has four columns: X1, X2, X3, X4. If you want to give names, petal length, petal width, sepal length, and the sepal width. So four columns are there. Whatever values you enter over there, depending on that, they will classify that data into three different categories. Okay, so the three classes of flowers which are present in that data set are: one is called as a setosa. Okay, setosa is one class. Another class is there which is called as versicolor, and the third class of flowers is called as virginica. Okay, anyway, I'm going to write it over there. Okay, so meanwhile we have a question there: is this a predefined data? Yes, as I told earlier, every each and every what you call library has its own data available, so that learners can use it. Okay, it may not be useful for any real time data or something. Okay, it may not be really useful, such as this particular data. You see, it is enough to learn something. All right. Okay, so the we already have assumed something. The assumption, first assumption, is that there is a learned model which is decision tree. There is a learned model available. So, and let's assume that I am trying to visualize that there is a particular plot. It is called as a tree plot. We'll look at that when we do the coding part. Okay, so the tree part is something very similar to what I'm going to write now. So every node there will be a particular feature. On a feature you will ask a question, so such as, look at this. So the question could be, because this is my parameter, this is one of the feature: petal length is lesser than or equal to 2.45. Again, this 2.45 is randomly I'm writing at random. Okay, so uh, again, it's obvious that we all know every parameter that we write here is of the same standard. Like if it is written in centimeters, everything will be in the centimeter. Okay, or if it is written in any other way like meters, millimeters, or whatever, everything will be the same. So you don't have to worry which unit it is. It's the same thing applicable for the complete data set. All right. After that, then there will be another uh, value written. This is called as GINI, Guinea. Okay. All right. So Guinea value will be calculated. I'll talk about the Guinea slightly later, because that is actually a training parameter, not during the testing. As of now, you understand what we are discussing is a trained model. So how this Guinea calculated, will come to that when we do the training part. Okay, so let me write some value here, 0.667 maybe. Okay, Then you have another parameter that is coming into picture, the samples, right? Let's say this is 150. I'll explain everything, right? But let me write it first. All right. Then we have values. So this is equal to 50, 50, 50, and you have class equal to, one of the class name will be displayed. Okay, SETOSE. So at a particular node, I need to understand that I'm going to see a question, something like petal length less or equal to 2.45. Question mark can be put up if human interpretation is required. Then there is a learning parameter called Guinea that is specific for a node. Then it says a samples, then values, then class. Okay. Now, so you see, you have asked a question over there, right? So once there is a question asked, there has to be answers. Normally, this question could be something like a logical questions to you. You may say that petal length for a test data. Now, this is a trained model. Okay, how the trained model looks like, I'm drawing that now. A visualization of a trained decision tree model. Each node you have certain questions, Gini score, samples, values, and the class. Okay, now, right, let's discuss this in detail slightly later. Let me complete the drawing first. Okay, so now you see, at this particular point, when I ask the question, I can have two answers. The first one saying that yes or true. Correct? True in the sense petal length less than 2.45 is a question. Answer is yes, true. So what happens? You move on to the next, say, node where you may or may not have to ask a question. Okay. Under what condition you reach there, I'll come to that. But let me write here. In this particular case, directly I don't have to ask any other question. I give a Gini score of this node that is 0.0 maybe. Okay, we'll write the second parameter that is samples equal to 50. Then I'll write the values, the similar ones. You are not writing only the question in this case. All right. So the value, let me write 50, 0, 0, and the class, right? I'll try to write that as setosa. I'll show you the complete thing now. So look at this. So petal length Guinea of the previous node you already have seen. That's a parent node, and the child node what you see here, right, is the new one. So in this case, I am not asking any question, right? Why, you will come to know in a while. Just hold on. Let me try to complete this. Okay, so as you see, we have created one child node out of this, wherein the answer to the question asked in case of the parental node is a true case. Okay, now let's say that there is another opportunity and the chance for us to get a false. All right, so this is a scenario where I say the answer to the question asked in the parent node is false. Okay, this could be no. Right. Now you see, in this case, I'll ask another question. All right. So this is petal width I'm going to ask now. All right. Less than or equal to maybe 1.75. How this question is framed, right? Who is going to decide that? We'll come to that. Okay. So this is a trained model. That's why I started with that. All right. We have a Gini score of this that is 0.5. How to calculate this value? I'll come to that when we discuss the maths. Okay, then you see the samples. Every node will give you the similar details with the different values present over there. Okay, then the value that is 0, 50, 50. Then the class is VERSI, color, COLOR. Okay, so this is the next thing that's going to happen. Anyway, I'm going to discuss this in detail uh, in a while. Let me finish the graph first. All right, so this is the level 1 of the graph. Now all classes have not been defined yet, so I will go further. Okay, I'll further split this into two more say nodes. I actually have asked a question over here. So when I try to answer the question, I'll definitely get one yes and one no. So if you say S over here, that is a true case. I come to this side wherein I'll say I'll calculate a Gini, right? Maybe this comes to be 0.17 approximately. We'll write the sample size maybe 54 and the value equal to 0 49.5 and class equal to versi color. Okay, let's assume this is our class. All right. Similarly, in the previous node, that's a parent node. When you say your answer is no, that is false. Okay. Our trained model resulted in following. Let's assume. Okay. So I have Gini that is equal to 0.04 something maybe. Then the samples equal to say 46. All right. Then we have value equal to 0 1 45 and the class equal to, it's called as Virginica, Ginica. So okay, that finishes drawing of our this thing. All right, let me show you this completely so that you can have a complete view of our decision tree which is learned. All right, so okay, this is how it looks like. Anyway, I'm going to zoom in, right, so that we can read and we can discuss further. But this is what is the plot of any learned uh, decision tree will look like. Now you see there is a particular parameter, right? What is the parameter I have used? I said that I'm going to use a specific value for our problem, that is max depth equal to 2. Okay, now can anybody guess what was that all about? Right, it's actually you can see that that's the depth here. So this is the depth 1, this is depth 2. Only 2 are sufficient to for our problem. Okay, so only 2 layers, 2, this is called as a depth. From the root node, how many times you can go in. All right, so that's the depth. So now you understand why we have used it. All right, so it's not wrong if you go for a higher value for sure. Okay, definitely you can go. All right, let me come back. So now let's discuss about this in slightly detailed fashion. Okay, now so you can see that at every node, right, you may start with a question. So the question is specifically asked to make a decision true or false. Okay, if you make it true, assume that this is it, this particular question which we asked, petal length is less than 2.5, resulted in a true, right? I can see no question asked here. That is because those who satisfy this particular condition, right, they fall into a particular class. You understood which class it is. You don't have to ask any other question. You see the class is decided, setos. Okay, right? Now you definitely ask one more question, right? Why there is a class named for the this one, right? So there is no answer for this node, but still the class says is said to be seto. Okay, so this is a general question I face whenever I teach this to my students. Okay, so the answer is like whichever the first class, right? You see, okay, I'll come to that slightly later. I'll answer that question, which I just now I only asked, right? So I'll try to answer, but before that, let me look at the other parameters. Anyway, Guinea is a score, right? We'll see that later. Samples 150 in the sense, right? In order to train this decision tree, how many total number of samples used, right? So in this case, let us assume that the 50 are from the class 1, 50 are from class 2, 50 from class 3. So totally how much? 150. So that samples equal to 150 means, right? That's what is used. But again, this is specific to the root node only. So right now we are in the root node. Root node says samples equal to 150. That means there are 150 training samples. Now after that you can see the values equal to 50, 50, 50. It should be very clear now. 50 from class 1, that is actually, right? This is how the ordering of the data has been happening inside the given data set. The class number 1 is actually setosa. The second 50 what you see here, they belong to the versicolor class, okay, and the last 50 what you see belongs to the virginica class. So 50, first 50 what you see, it's actually from the class setosa. All right, now I'm answering that question. Though there is no class defined, right? You are not coming to a conclusion about any class in your root node. What is this class equal to setosa doing here? Okay, so the answer is it's the built-in way of in which the coding has been happening inside the decision tree classifier of sklearn. It always prints the name of your first class. So first class is what? It is setosa. That's why it will print. Okay, same rule is applied even for the next layers, next depths also. Depth equal to 1, depth equal to 2 also, you will see the same thing happening, but I'll come to that later. Okay, so I hope the root node specifications of the display is clear. All right, let's move further. Let's go to the next layer, that is depth equal to 1. When I say depth equal to 1, only till here the tree will be plotted only till here. Tree will have only one layer, that's all. Okay, from the root node there is one branch coming up ending in two nodes. So one for a true, one for false. Okay, you see the true, you don't have to ask any other question because that itself is the question asked in the previous node itself is sufficient to make a decision, right? How the machine could understand that, okay, if this is my first question, we'll answer that. Okay, we'll come to that later. So let's say it's a trained model. The true decision taken from by checking at that parameter says that, okay, if a testing sample satisfied this particular condition of the petal length being lesser than equal to 2.45 is a single question that is sufficient to put a label on that test dataset as a setosa class. Directly it will be decided. So since there is no question needs to be asked, you don't have a question over here, right? So there is no question here, and right, I can also, right, understand that Gini score will be calculated. Samples are 50, so that 50 comes from here because those 50 are, right, have been used to train this particular node. Okay, so value means all the 50 are belonging to this class, no other class. Okay, so that's what is meant by value, and you have a class. So move further, right? When the question asked in the previous node results in a no, right, in a false, I'll move to the other branch. So there you may have to ask another question because there are basically there are two classes which falls under this particular answer false, correct? So that means I may not be able to finish my tree here. I may have to go further. So petal width is less than or equal to 1.75 is my next question. All right, so corresponding to this question we'll have a Gini score, right? How many samples are remaining? That actually 50 plus 50 from the previous this thing, if you check, right? So you have 50 plus 50 samples, so totally that's 100. Okay, so that's why the 100 is the samples equal to written over there, and you can also see the values are 50 50 from each class. This is not there, so now the first class becomes this 50. That's why that class is given the name printed over there is belonging to your second class, because first class already has moved to the left side. Now the second class in our actual values becomes the first class. That's why the second class itself has been printed over. All right, moving further, again a question is asked. True means you come to this side, false means you go to the other side. Okay, now you don't have to ask a question because true means it is one class, false means the other class. So asking a proper question itself is the main hint over here, right, in building the decision tree. So that's why we said that it is a data driven. You see, no parameters, no theta value, no theta 1, theta 2, theta 3, nothing. Simply you have a data, get a proper insight of the data, formulate the questions in the form of layers of a tree. You call it as a tree. You ask a question one by one. If yes, no, make a decision, right? Depending upon. Okay, so the fundamentals of decision tree is pretty straightforward, right? You don't have to do rigorous mathematics over there to find out various parameters. That's why no parameters, so this is non-parametric model. Okay, so we are open for questions. So far, whatever we have discussed, if you have any doubt, please go ahead. So we'll move ahead. Now we'll see what happens if a new data point, right? What happens if a new data point comes? Again, this is a classification problem. All right. Okay, so we have a question. How long can this tree be? Right. So depends on your data set complexity. Now you see in this particular data set, we have only 4 columns. So the number of features are pretty much less. But when you go to a practical scenario, number of columns can go thousands, 10,000 or something. So, right, we can go to the trees up to layers like the depth of trees can be 100, 200, etc. All right. So you can add any number of layers until and unless there is what is called as overfitting. All right, so we'll discuss about the overfit as well, right? Until and unless there is no overfit, there is no harm in increasing the number of depth. Okay, depth value you can enter. Again, I will show you how. Okay, I think I already have written that in the code, right? Depth you can predefine, or otherwise there is a fixed value which it will use. Okay, all right. Now, so we have done the visualization part. Okay, so that was our second point. If you remember, visualize the dt, right? How a pre-trained, after training, how the decision tree is going to look like, we have seen. So that is actually a plot. By using a command we can see that. Okay, in the scikit-learn. Anyway, we'll touch that when we do the coding part itself. But as of now, I just try to draw something by myself. Okay, now so the next part, the third part we'll enter, that's a prediction using the decision tree. Okay, so how the prediction is going to work is what we will be seeing now. Okay, let's say what happens when a new data point comes. This is again for a testing purpose. So this means you are doing the testing. Okay, so we are doing the testing. Let's say the petal length value is 2, maybe 2.0. And let's say for the new data point, the petal width is 1.0. Okay, so just check, just go back and check my first question. So is the petal length is less than 2.45 is the first question that it asks. As soon as you see a new data point, you will simply ask that question. Okay. Now what happens? Answer is true, right? So as soon as right that happens, it will classify. Your data will be directly classified into Setosa. All right. Let me go to another part. Right. This is another example. Let's say the petal length. Petal length is equal to, let me make it 3 now, and petal width is equal to, let me keep it 1 itself. Okay, so 3 and 1, petal length is 3, petal width is 1. So the first will say false, so it will come to the right side. Okay, and you can see that petal width is 1.5. So what is a petal width? Petal width is 1, so it is less than 1.5, so the true, so it becomes the vesicolor. All right, that's the class. So class gets right labeled as quick as that. Right, so this is what has happened. Right, the first question that asked here, right, for the first one, it checked that right, what is the petal length? That was my first question. Less than 2.45, so your answer is right. Yes, so yes means you move left, and as soon as you move left, you got your answer. Right, that's why you ended up in the set of sum. So for a next case, right, for the second case it was 3, so you move to the right, but after right you ask one more question, that is about the petal width, and in case of the petal width the question was less than 1.5, so it is the actual value is 1, so you said true, and true gave moved you to the left for the true path, and you got an answer, that is C color. All right, okay. Now, let me quickly write a point over there so that when you read this material, the thing should be clear. Okay, so now for at each of the node that you face, right, at each of the node from top of the tree, what you will do, right, ask a question. You have to ask a question, right? Ask a question, comma, you have to move down on a specific path, that is based on the answer to that question, right, depending on what, depending on the data set, right, data, if it is a testing data, you will use that testing data point itself to answer this question, okay, following a particular path. So normally, according to our case, our this particular problem, our graph, right, of the tree, maybe the if the answer says true, you will take the left side path. If it is false, you will move to the right side path. Okay, again, this is just an example, right? We'll see the actual trees when we plot, when we do the coding and when we plot. Okay, now once this is done, I reach another node, right? I have to keep moving. So you need to keep moving until, right? Until where? Until you reach the end That's called as a until reach a. Okay, I can write leaf node. So how do you identify a leaf node? Leaf node is something, right, from where you don't have any path going further. All right. So leaf node. So what do you mean by leaf node? Let me try to write that. That means there is no children to that. All right. Now, how do you identify the class? The class of the leaf node, a data point ends itself is the class of that particular data point. All right. So I write the class of the leaf node, a, a data point ends up in its class. Very simple. So working out is very simple. All right. So whenever our intention is to classify, right, there is a trained model and you want to do a classification by doing a testing of the testing data sample. This is how it's going to work. All right. So let me also show you another picture of the classes in terms of the decision boundaries, let us see. Okay. So let me try to bring a 2D plot, maybe that's going to help us. So let me say for the same problem which we have been solving so far, right? I'll write the petal length along this, and I'll just write PW here. That's a petal width, okay, along this. So petal length along x-axis. So this is 0. So maybe you have few values written. 0, this is 1, 2, 3, 4, 5, 6, 7, 8 maybe. So 0, sorry, that's started with already started with 0. Let me put 1, 2, 3, 4, etc. Okay, 5, 6, 7, dot, dot, dot. And vertically also I'll write some of the values like this. If this is 0, maybe this is 0.5, 1, 1.5, 2, 2.5, 3, etc. Okay, this is 0.5, 1, 1.5, 2, 2.5, 3, etc. All right. Okay, so the first question that you asked was petal length less than 2 point something. So petal length being less than 2 point something, maybe I'll take it as around 2.5, is always this. So any data point that actually falls over here, right? So if you have any data point that falls over here, okay, it may not be like this. Actually, when you plot it, you don't get so many points. I think I'll show you that at a later stage. Okay, so somewhere here you get all the values because something like this. Then the second question asks, so if at all your petal length is less than this, it's always this category. Then whatever is not no for this, that actually lies here. So this is a true, this is a false for that question. True means on the left side of the line, false means on the right side of the line. So that's how the actually that one question itself splitted your data set into one proper class and another class containing all other classes. That's the other two categories. Now you see we asked another question saying that the petal width is lesser than in the among the false class we got earlier. We asked another question. Are so is the petal width is less than, I think 1.75. 1.75 is where somewhere here. Let me see. Okay, this is 1.75. Okay, if at all, this is the second question. All right, so petal width is less than 1.75 is a question. So if it is yes, you see you reached another class. So maybe those points are somewhere here. So it has nothing to do with the petal length less than 2.5 or something. So it's more than that. So already decided. You don't have to check the petal length once again. Just check out what is the petal width less than 1.5. Yes, that's this class. So that means I still have a no, right? Possible. So when I say that there is a no that is possible over here, that means it should fall under the third category, right? So which can be this class. Right? So that's how you see the decision boundaries are actually ultimately, if you see, still it's actually trying to, in this case I'm trying to make you to visualize in the form of a straight line, but right, because x is equal to 4, x equal to 5, y is less than 5, y greater than 5, etc., are actually can be simply classified by using the straight lines. All right, so that's why these decision boundaries will look like what is called as a linearly separable classes for sure. But yes, right, again this is a visualization only, right? Complicated data when it comes into picture, right, you will definitely have a very complicated boundaries coming into picture. We will be able to visualize that as well, right, when we see. Okay, so do we have any questions with this so far? Whatever we discussed, is there any question? Please go ahead. Okay, so that's good. Let's proceed further. Now, the next objective here is we'll look at the maths behind. All right. So my next point that I want to discuss now is right. This is all about understanding the DT, the decision tree properly. Basically, we look at various attributes of the decision tree. So the first one, it's called as, already we have used this name. It's Gini score, right? Basically, right? I don't know how the name came as Gini, or is there any specific meaning behind that? I have never explored that much. Okay, so those who are interested can try to find out and explore that. And if you get an answer, please tell me. I'll also learn something from that. Okay, so I never worried so far about what is the meaning of that, or is there any meaning of that. So, but what it actually does, it is a measure. It's a it's a measure of what is called as a impurity. Okay, of a particular node. All right, what do you mean by impurity? Let me go back to the drawing of the tree. So look at the, okay, I'll come to, I'll start with the this part. Okay, so on the left hand side, this, the branch which went to the left side saying true said Guinea equal to 0, right? I'll give an equation to calculate that. It's not possible to calculate it straightforward by just looking at this, but let me show you what is meant by pure node and what is impure. Okay, so for that reason I'm trying to explain this. So you see here the Guinea says 0, right? It says I have 50 samples and all the 50 samples belongs to the same class called Setosa. That's why it is pure. Look at the other side. That is on the false part, right? You can see that there is a question for sure. Guinea is 0.5. Whenever you see Guinea value exists, means it is impure. Guinea 0 means pure. So you see Guinea is equal to 0.5 in this case. So that indicates what? Somehow it is a impure node. Why it is impure? I have 100 samples, out of which 50 belong to one class, 50 belong to other class. So it's not a pure node, right? Will it be pure even in the next case? Not necessary. You see, Guinea is equal to 0.17 for one case, 0.043 for other case. That is because no pure values exist. Out of 54, 49 is one class, 5 is the other class. Again, for the right side, that's a false node. You see Guinea is equal to 0.043. Out of 46 samples, right? One sample for one class, 45 sample for other class, right? So under what condition you get a pure node, you have an idea. Under what condition you get impure node, that also you know. So what is meant by impurity, right? Now you can actually get a definition for yourself, correct? So Gini score becoming 0 like this, right? What you see on the left side, top left corner, that is a pure. So Gini becomes 0 over there because it's a pure value. Or whatever values you have, it's for only one class and you are able to make a decision over there. And there are other nodes, right, which can have a Gini value, right, which indicates that there is some kind of impurity present over there. So that's why we wrote one point here saying that the Gini score is a particular attribute of our decision tree which actually is used to measure some kind of impurity. Okay, now let me try to give an equation for that. All right, so the Gini score of a ith node is given by, it is 1 minus the summation, right, of the k varying from 1 to n. Okay, I'll write p I comma k whole square. Okay, let me write what I'm trying to denote over here. So the p I comma k. So when I write p I comma k, right, that basically I'm trying to write the fraction. It's a fraction. Okay, fraction of the kth class. There are k number of classes. In the previous case, that is 1, 2, 3, 3 classes. K equal to 1 for first class, k equal to 2 for second class, k equal to 3 for the third class. All right. So that's what we are writing. Kth class in uh, in the ith node. All right. So that's what k and I stand for. I have another n coming into picture in the equation. N is the total number of classes. So in this case, n is equal to 3 itself. N always remains 3. Right? But k takes values 1, 2, 3. K equal to 1, k equal to 2, and k equal to 3. Okay, so that's one very important parameter. Again, we will see this calculation being happening. This will be done during the training part. Okay, so how that happens we'll see later, but let's try to learn how to use it first. Okay, how this equation can be used to do the calculation, right? We'll see that. Okay, so let me copy something first so that I can show you the Gini calculation. All right, so let me go to uh, a particular node. Okay, okay, I think this is where we can start from. So I will start the calculation. Only one or two nodes, let me show you. Okay, others you can extend that and you can do it by yourself. So but let me try to start with this. So you know which one I actually have copied now. So let me try to paste it over here. Okay, so this is what we have here. So let's try to calculate a g value. Okay, so this is ith node. Any I can be anything. Okay, don't worry about that. So let me try to write a gi here. That is equal to 1 minus, I need to write the summation, right? Summation means I can put a bracket and I can keep adding the terms. So I just have to look at these numbers. You see, I'll show you the equation once again, just for your reference. It should be p square. P is a fraction of a class in the ith node, right? What portion of your data set belongs to that class? So this node, if you see, 0 by 54 is the first class. So this has to be 0 by 54. That is a fraction. It's a square. Plus, what is the fraction of the second class? 49 by 54. It's a square. Plus 5 by 54. It's a square. Is it okay? Very straightforward equation. Let me know if you have doubt. Meanwhile, those who understood, please finish the calculation. Okay, give me a value. Please type your answers in the chat box. Okay. Anybody who got answer for this calculation? Okay, so Harshal says answer is 0.168. I think I have approximated that. So Guinea score I have written as 0.17, but let me write your answer over here. Okay, so that comes to be 0.168. Perfect. Others, please verify you the answer that we are writing here. Okay. Maybe there will be a very slight changes possible. So you can see that the Gini score is being calculated in this particular fashion. Okay. While everybody is doing the calculation, right, we'll break out for a tea break of 20 minutes. So let's come back and join at 5:50 p.m. and we'll continue the discussion on decision trees. Okay. Everyone, take a break and come back after, say, 20 minutes. So far, uh, we had discussed about what is meant by non-parametric learning, and decision tree is a part of non-parametric learning. And uh, what are what are the various attributes that are required to build the decision tree? So, in order to understand that, we initially started with a trained model, and what are the various attributes that are present over there we saw. And when a model is trained, how the testing happens, right? Right, based on the various parameters of the model, right? And depending upon the data points, right, we can ask some questions and we can flow through, right? We can go through the tree that has been designed, okay, has been modeled. That's what we have seen. And after that, we also have seen how the decision boundaries will be created by those questions, right? That's also we have seen. Then we move on to the Gini score. We understood that there is a concept called impurity of a node, and that can be measured using the Gini, using this particular equation. Okay, so and then we saw that one example of calculation of a Gini All right. So now I'll give some value so that I want you to calculate the Gini scores of the for the following examples. All right. So let me write the example values. So let me say the samples for a node, the samples is say value of samples 46, and the value, okay, value is equal to 0, 1, 45. So please calculate the GI. Everyone, please calculate the value of the Gini for this particular node and put your answers in the chat so that we can discuss. Okay. Okay, we have one answer. That is 0.043. We'll verify. Others, please put your answers in the chat. Okay, both answers are pretty much close. Let me write this value 0.04347. All right. So considering to be the 4 decimal places, we can truncate to this, I guess, or 435 should also work. Okay. All right. Others, please calculate and verify your answers. Then I want to give another value, let's say. So this is the next example wherein the samples equal to 100 and value equal to 0, 50, 50. Okay, please calculate the Gini score of this particular node. Yes, Upkar, your answer is for the present question or the previous one? 0.0425.
Previous one.
Previous one, right? Okay. Maybe uh, maybe can you try once again, because the answer which I have is 0.043 itself. 425 can be approximated to 0.043, I guess. Okay, that's also fine. Okay, so we have one answer, that is 2 for the present question. Others, please verify, please calculate and put your answers in the chat box.
So the last value, is it 50 or 56?
50, 50. Both values are 50. Okay, so 0, 50, 50. Okay, so we have two different answers for this particular question. It's 2 and the 0.5. Others, please do the calculation and put your answers in the chat. I think it may not be 2 because you will be subtracting something from 1, right? So it's not going to increase. It's not going to be more than 1, I guess, because the fractions can be highest is 1. So 1 minus 1 will be 0, or the fraction can be 0, in which case answer will be 1. So I'm expecting something lesser than 1 in this case. Okay, so 50 by 100 whole square plus 50 by 100 whole square, right? So 1, you need to subtract that answer from 1. So expected value is definitely lesser than 1. Gaurav, can you verify once?
Sir, can you go up? I just want to see the equation.
Yeah, this one.
No, not this one. The actual GI equation. Yeah. Okay. One. And okay. Sure.
All right. So
Mm,
this will be something like 1 minus first value 0. Next value is 50 by 100 is 1 by 2. It's a square plus one more 1 by 2. It's a square. Correct. So 1 by 4 plus 1 by 4
Yeah.
is 1 by 2. 1 minus 1 by 2 is half. So that will be 0.5. Okay. Yes. Harshal has given. So 0.5 is what we expect. Right. So we were trying to understand the various attributes of the decision tree, and in which the first one we considered is the Gini score. All right. So after that, if you look at the various other parameters or the attributes of the decision tree, we have one parameter that actually is set to be samples. So for every node, we can see this attribute. So this is the number of training instances. Okay, it's a number of training instances. I can say that it's related to a particular question. So let me try to write it in the same sense. So number of training instances for which this, or I can write for which I'll write this question was applied. Okay, this makes more sense. All right, that's about the samples. For every node, we'll see these attributes. Then we have another one called value. So what's value? How many training instances of each class this node is applicable to? That's what we are trying to write. All right, so this is we are trying to write how. how many training instances of each class. A particular node applies to. Okay, then we have fourth attribute for a given particular node. It's actually called as the class. So the label which will be applied to the instance if we stop at that point, right? At every node, if you stop training, right, which is the particular conclusion that you can come to, or the label which will be applied to the instance if you stop at that particular point. Okay, so let me try to write in the same way. This actually is the label. It's the label. It's a label which will be applied to the instance if we stop at that particular. Okay, all right, so these are the various attributes that one can find for each of the given node, right, of a decision tree. So after this we'll move on further, and let's say the next point that I want to discuss here will be related to the interpretation of the model. So how can one interpret the model that right has been designed? So right, so I can write the model interpretation. Okay, now as far as uh, the classification is considered, or the prediction by use prediction of any testing data, testing sample by using the decision tree is considered, we already have understood that the prediction or classification is very easy to interpret through the decision tree, right? Because already we have seen that one, if you know what are the rules, even humans can simply apply that. In a sense, manual application of the rules are possible, and it is very easy to understand. Correct? It's not a very difficult job. So the talking about the interpretation, we can simply write one sentence over here. So the decision tree, right, is easy. Okay, easy to interpret. Right, we already know this. Right? The rules can be applied manually. You can apply it manually and easy to understand. I'll write and understood. Okay, coming to the technical terminology, any model, any data model, right? Any data model which is of this type, right? we manually can easily understand, easily interpretable, and the rules can be applied and understand what exactly is going to happen if we are able to do uh, such things, right? So this particular kind of models are actually called as the white box. Okay, it's called as a white box model. So you might have heard of a black box model, correct? What do you mean by black box? Anybody? Can you guess what is a black box? Like we say that, right? Whatever, right? You give an input, you get an output, right? But the model is a black box. We'll say that, right? So black box is a detailed model. Okay. Anybody else? Please try. Uh, because you might have heard of the word black box several times, right? I'll tell you why the decision tree is called as a white box once again. For a given test data, we manually can see what is happening, right? A particular parameter is compared by asking a question. You say yes or no, move along a path in the decision tree, go to the next level, okay, next depth level. You ask another question like that. It's possible to do that particular job manually, right? It is easy to interpret. It is every rule you can apply, right, manually, and you can do that. Now that's why it is called as a white box. Means what will be the black? It should be the opposite, right? At least. So which is more detailed? Is white or the black? For example, let me tell you something more, so that uh, you can guess the answer, right, more accurately. So for example, if you consider the neural network or even the random forest, all right, which is the next version of the decision tree, we'll come to that maybe uh, after some time. So in case of neural network or maybe the random forest, they are considered as a black box models. The reason behind that could be something like it is really hard to explain why a particular instance is classified as a particular class. It's impossible to trace it out. Okay, so you cannot trace that, right? So you are able to trace it in this case. In the decision tree, you are able to trace it out. You have a very strong answer saying that why this particular sample is belonging to a class, because you know what questions are asked and what is the answer, right? Yes means this is the answer, no means you move to the next level, ask another question, yes means you have an answer, no means the other answer. Like this, you have a very justified way to defend, right, the classification. Okay, so again, that can be traced easily. Manually you can do the calculation and it is easy to interpret, right? So that's a white box. It is not going to happen in case of the black box models such as neural network, random forest, etc. Okay, so now you have an answer, right? Well, now I think you have a very clear idea that what is a white box model. Again, this is a technical term. Okay, so if you use the references or the internet resources, you will find these names. So I don't want you to get confused. That's why I also brought these names into picture. Okay, so this is something like an advantage you can consider, right? It's a good point about the decision tree. All right, so another point which I consider as a as an advantage of decision tree is that, right, normally you don't have to perform any scaling. All right, so dt doesn't need any sort of scaling, okay, of the data. But other models, we already have come across the scaling part as well, right? We have seen, okay, we have seen the scaling that is happening for various types of algorithms, which we already have come across. Again, this here you see it's a question based, right? Whether you scale the data or you don't scale the data, right? Uh, it's not going to affect. Okay, so it's not going to affect your. So scaling is basically not required. And one more very important feature that I observed is that right DT handles the missing data, right? Which means even if there is a missing data, a particular column is right. It's a missing data means doesn't matter. All right. So this means I can write. Sorry, I can write. No need to fill. So fill NA etc. is not required. You can save some of the computational time. That's all. Okay, this is what I have observed, right? Even if you don't do that with the other some other parameters, right, which actually present in your data set, it can still do a calculation. Is that okay? So those are some of the important features. Okay. Now, as far as the implementation comes into picture, the sklearn has a card algorithm present in it. Normally, this sklearn is able to produce only the binary trees, like only yes or no questions can be asked, and you can try to generate the trees based on the binary logic, yes or no kind only. All right, but if at all you want to go with more than two children, okay, for a given node, we may have to go for other libraries. Okay, so that's what is the input that I can give. All right, so with respect to whatever we have been discussing so far, all right, let's go for a quick question. All right, give me 1 second, I'll bring up the questions. Okay, we'll have a quick quiz just to understand how much you are able to grasp about the various topics we discussed just now. All right, so question number one, both questions are true and false kind. So question number one, you just have to answer T or F. Question number two also, you just have to answer T or F. We have few answers coming. I want everyone to participate in the quiz. Please put your answers in the chat. Okay. To answer this question, the first one says the decision tree is an opaque model. So opaque means non-transparent, right? So we know that everything that happens inside the decision tree is known to us. We can trace it out, right? So it's a opposite. Opaque is opposite of transparent. So it says it is non-transparent. Is it true? It's not true, right? It is actually a transparent model. So the answer is false, right? And the second one is much more easier. It can classify only linear separable data. No, it's actually, it is capable of solving, or it can classify even a uh, non-linearly separable data as well. All right. So because of that, the answer to the second question is also false. All right. Let's move further. Now we'll come into the important part of the training. Okay, so far we never looked at the training. Now we are considering the training that happens through what is called as the cart algorithm. Okay, so I'll just write the step-by-step procedure. I'll write a step and I'll explain that. All right, so step number one is, normally you have a training data with you. Now, at every node, right, depending upon the x value, and you will decide a threshold. How to come to a threshold, I'll come to that, right? You will split your data set into two parts. That's what we have seen earlier, right? For example, let me go back to the diagram that we had used earlier. At this particular node, right, what you are basically trying to do is that you split your data set. Data set is 150. That's the total number of data points you have. You split that into two parts. You see, the two parts are, sorry, what are the two different parts you have here? 150 is split into two parts. One is 50, one is 100. So this is what is the first step. Okay, based on what we split, we see that there is a threshold that is coming into picture, and all my samples are denoted by x. Every sample x either goes to the left side or the right side. Again, I am considering only the binary class, okay, binary type of the tree. But yes, you can use other uh, libraries if you want to go with the, right, what is called as more than two branches or more than two children, right, in case of the decision tree. Okay, so the first one is, first point I can try to write in this way. So that is, at each node, we are going to split the training data set set into two subsets, right? Based on what? Based on one value and one value of, I will call it as a feature, one value of a feature. Okay, like the previous case, we had 4 different features in our data set. That is petal length, petal width, sepal length, sepal width. But based on only one thing, petal length, I decided something. So that's one single value of a feature. All right, so I'll call that as xk. Xk is one that, and a threshold. Right, so let's denote tk on it. Right, how to decide that? I'll come to. How do you come to know about a tk? Right, because that's important. Xk can be selected, but how do you come to know that the petal length is less than 2.75? Right, so that's what is important. So to justify that, I'm going to step number 2. Right, so you can see that uh, xk and tk can be considered as a pair, because machine has initially, it has no idea that this is a particular feature and this is the particular value of the threshold. What it does, it will actually try to do a repetitive process, right? Right, repetitively it will calculate every possible xk with every possible tk on it, right? Because it knows what is the range of tk, right? If you see the data set, the for example, let's say I'm looking at a feature called petal length. Petal length may be varying from 0 to 4. Okay, in the data set it is 0 to 4, so you don't have any infinite values to check. So start from 0, go with the step by step and check whether that particular xk and tk can be selected, right, as a particular question in the node. But I cannot simply say that. I have to give a mathematical notation for that. So this is how it looks like. All right, so I'll create a pair. So the pair, I try to denote that pair as this, that is xk comma tk, right? It is, how do you choose it? So it is going to be chosen by what results in the purest subset. So you know what you mean by purity, right? Because that's why we calculate a Gini score, right? Out of all the possible subsets that you can split your main data set, I had a 150 data, right? I try to split it into different ways, out of which the 50 and the remaining 100 is the purest one, because you see 0 score coming up over. That's why it was 0. It automatically, right, iteratively, it actually has identified this particular process. I'm going to give the equation now. All right, so purest subset uh, measured using an entropy equation. So the equation that you are going to see now is called as entropy equation, that is denoted by j of xk comma tk. So xk tk is a particular pair. So you see we have m left divided by m into, this is g left. I'll justify what I'm writing. Okay, then m right divided by m into, this is g right. So if you are located at a particular node, what are the various parameters that you can measure? So that's actually I can consider as a kth node. All right, so I can definitely split this into 2 parts, right? So this is the left, this is the right. Okay, so if you totally have let me write the xk tkr right? The pair which we are considering right now, right? Let me assume that there are total m number of samples for a given kth node, and definitely this is what this is what results right after the split. So definitely I have m number of right samples in the left space. That's why we call it as m left. Okay, similarly you have m on the right side, you will be having m, sorry, this is m right. So you will have the values right corresponding to the left side. You will have a value left, value right. Definitely I can write the g left, right? That's a guinea for the left data, and this is the guinea for the right data. So m left, m right will generate the value. Okay, using the value you can calculate a g value. Okay, that's a guinea. So now you see I can definitely right calculate the entropy given by this. So what is the use of this? This is the mathematical equation that has been suggested by the researchers who invented the decision tree, right? So their approach is that you calculate a entropy for each set of x and tk, right? Xk and tk that you select, right? And what you do, right? You have to select the one which gives the minimum value of this, right? So just I may have say 50 different options of xktk for uh, let's say for my data. Okay, for a given data I can say that I have 50 different options, out of which whichever j, this value j of xktk is minimum, right? You will select that. That's the one which have the minimum guinea value, correct? So that's how you select. So let me just write the G is impurity, and M is the number of instances. I think that is very clear. I don't have to write. So select the minimum one, right? And make the branches out of it. Then simply repeat this. So continue the same for the two child nodes you have. Okay, continue the same for children nodes. Now we have a question when to stop. Okay, so stopping condition is like this. So stop when no further split reduces the impurity. So impurity, even after splitting after a particular level, you will see that it's not going to reduce the impurity at all. Impurity remains the same. That means that's the time to stop. This is the condition number one. Or otherwise, there is another way to stop. So that is you reach the maximum depth, like our case. So maximum depth is reached. So to decide the maximum depth, you can also use the cross entropy. Already we have defined the cross entropy in the previous session. You can use that. Okay. So if the cross entropy is already right, a particular value, you can just stop it over there. All right. So using these techniques, right, you can stop the creation of layers or depth of this thing. So further splitting can be stopped over here. So this is what happens inside the main uh, training algorithm that is used in the decision tree called classification and regression trees. All right. So let me know if you have any doubt with this. Otherwise, I will go further. Okay. So the next part that comes into picture whenever we try to implement the decision tree is called as the regularization. Okay, now this regularization is a slightly what you call slightly different compared to the regularization we had discussed. We have been discussing in the previous topics. That is because, do you have any parameters associated with the decision tree? So the answer is no. We don't have any parameters that are being used to define my model. I don't define my model in terms of I don't use any theta naught, theta 1, theta 2, etc. There's no question of any parameters. So that means decision tree is a non-parametric model, right? So I know this. So decision tree, I can directly write is it's a non-parametric model, right? In the sense, if you use any other model, like we have so far come across a linear regression, right, or the logistic regression, wherein you see that they are something like a linear models, and they are parametric. You have a predefined number of parameters for that, correct? So if you know there are say 6 different columns in my data set, you will have 7 parameters that is predefined. Okay, so that's what the case, right? Now, since you don't have the specified number of parameters that are supposed to be used for this kind of models, it is expected that uh, decision tree DT can overfit your data. Okay, so to avoid overfit, what we are going to do, we are going to use a uh, will specify what is called as a degree of freedom. Okay, there is a concept called degree of freedom. So I'm going to define the degree of freedom now. Why do you use it? It's used to avoid the overfitting. So let me write about overfitting first. uh, okay, the DT can overfit training data. So if you want to avoid that, right, so to avoid overfitting, the only solution we have is restrict the degrees of freedom. Okay, what do you mean by that? I'm coming to that. All right. Restrict the degrees of freedom of the decision tree. So what are the in order to restrict, right, or in order to uh, avoid the overfitting, we have to perform we have to limit the degrees of freedom. So this restriction itself is what we are going to call as the regularization in this case. So regularization basically refers to restriction of the degrees of freedom. Now, what are the degrees of freedom, right? It's the it actually the uh, degrees of freedom basically refers to the number of hyperparameters that you use for the regularization, right? So that is uh, by specifying the following hyperparameters. So what are they? Now the first one is already we have seen, that is the max depth, right? So what is max depth? Maximum number of levels. You can specify this. All right. Then we can also specify the second one is there is a minimum value for sample split. Minimum samples split. In the sense, minimum number of samples at a node that must have before it can split. In the sense, you can specify, right? Like if you don't have the numbers at least 50, you stop. You don't have to go further. This is what you can specify, right? So if you don't specify, it keeps on further dividing. Maybe that's the one which results in the overfit. Okay, so like minimum, you can also have the maximum. Okay, so let me write a point over here. So this is the parameter. So let me try to write minimum sample split, minimum number of samples a node must have. Okay, before it can split, this is the minimum number of right samples that must be present. Okay. Pardon me, Devendra. There is slight net issue over my side. Okay. Let me know if you want me to repeat anything. I can do that. Uh, Sorry for the inconvenience caused, if any. Okay. So this is the minimum number of samples, and let me go to the third one. So the third hyperparameter is min samples leave. Okay. So that is min again. This can be specified. So minimum number of samples a leaf node must have. Okay. So this again talks about the minimum number of samples a particular leaf node must have. Okay. So then uh, we can also define one more very important parameter, the fourth one. This is called as a minimum weight fraction. Again for a leaf. So as we can guess, this is nothing but uh, we already have a minimum samples of a leaf. That's the point number 3. If you try to represent that in a fraction of the total number of what you call weighted incidents, all right, so it's a fraction. You try to write the previous one in a fraction format, that gives you this. Either of them you can specify. Okay, so I'll just write 3 written in the fraction form gives you this. Okay, so those are the fourth important one. So as the minimum can be specified, the fifth one could be the maximum number. Why should we specify only minimum? Go with the maximum also. So I'll just write the name, so the meaning is very clear. So simply write max leaf nodes. This can be specified. uh, then even the max features can be specified. So maximum number of features that you need to evaluate throughout the process can be specified, then you have something called as right. Okay, the 6 parameters, right? Those are the 6 things which we are specifying. Now, what can we do? Okay, so how do you say that by using all these parameters? How can you justify that I'm doing a regularization and I'm trying to avoid the overfitting? So that's by using this point. All right, so this is you have to increase the minimum value parameters. Whatever is minimum value, right? You try to increase that. Otherwise, you have to do the reverse. That is reduce the whatever set max, right? You try to reduce that. Okay, maximum. Okay, it's a hyperparameter, but let me write parameter. So if you try to keep changing these values, right? Whenever you observe a higher, whenever we observe what is called as overfit that's happening, right? For my data, I'm supposed to either increase the minimum parameters in my out of these 6 points I have written, and you can also reduce the max parameters that have been defined. So whenever that happens, you can say that yes, you are performing what is called as regularization, and you know the uses of regularization. As the regularization proceeds, right, we know that machine learns in a much better way, and right, we can say that the classification is going to happen in a smooth way without any of the hyperfits. Okay, all right, so this is what practically has been observed, right, in various projects. Okay, now let's come back to, so we already have seen the advantages, right? Let's try to look at the some of the issues. Okay, so right now we'll be looking at what are the various issues. Okay, now okay, can you guess? Anybody? Can you suggest? What do you think? What may be the issues? We said that this is pretty straightforward, very easy, etc. Correct, but anyway, every method is expected to have some drawbacks. And what do you think? What do you think? What can be done? What is the issue? Maybe you can think of that, and later on we'll think about how do we overcome. Yes, we have one answer from Ruchi. It says that exact information requires to define the decision boundaries. In a sense, exact information in terms of your data points, right? Data points are the ones which are the only resource of the information. So that information needs to be very precise, right? So I think that that's what is the meaning, correct? Right? It's a most appropriate answer I was expecting. So you see, we can say that the decision tree basically generates decision boundaries which are something like orthogonal, right? So they can be separated. The okay, I'll just go back. Just go back. this kind of representation is orthogonal, right? So you see, right, this is orthogonal, this is orthogonal, etc. So the boundaries, decision boundaries defined by the decision tree is basically orthogonal. Again, that's a technical term, right? It's fine, even if we don't get that, that's absolutely fine. But what's the problem? The problem with that is, if you slightly modify your data, right? Again, I'll bring another technical term that is said to be convoluted. So this is the problem. Problem number one that we face is uh, maybe rotating the data. I'll justify this. Okay, makes the decision tree convoluted. Again, convoluted is a technical term. I'll just try to uh, give an example over here. So this is for the first set of training data, and I'll try to draw the another set of the training data. So let me try to write two classes over here. Okay, so this is say class 1, maybe this is how it looks like, let's assume. And the second class is something like this, maybe, let's assume. So we can see that in this particular scenario, the decision that will be made by this is something like this. Okay, very straightforward. But now you see, what happens is I slightly make a rotation. Let's say that my data set is slightly rotated in this particular fashion. Okay, again, we are not making this, right? It is automatically, this is how it's happening, let's say. Okay, so my data set itself is like that, that's all. Okay, so same thing I'm actually trying to rotate, let's say. So since you are trying all see, since you are making the decision boundaries on orthogonal principle, right? So maybe our first, let me try to write this. This may not be very appropriate what I try to draw here. So maybe this is how it will look, I guess. This is how, I guess. It may not be very appropriate to see. Okay, I'm not able to show that. Okay, let me try to back. Let me try to undo this thing. Okay, let me also try to undo. Let me try to draw by hand. Okay, so maybe something like this will happen. Okay, so something like this. So you see that unnecessarily there are a lot of right decision boundaries. It's making it very complicated. That's all, right? So convoluted basically refers to that. So something like this, something like this, maybe like this. It will miss some of the values maybe, and it will be doing like this. You see that this part, the horizontal part which is present over there, and even this part, etc. Right? You can see that that's an unnecessary part. So the technical term for this kind of decision boundary is the convoluted decision boundaries. So if your data set is like this, though you can classify something like this, it is not able to do that. Okay, it will not do that. So that's what has been observed. Okay, mathematically I cannot prove this. By solving something I cannot prove this, but this is what has been observed. Okay, so that's the first issue, that is with the decision tree. Anyway, there is an option called using principal component analysis and right, many other things which you can apply to make it simple. Okay, to resolve this issue, we have a solution like that, but uh, that's not a suggested one. Okay, because you are making things more complicated. So see, that's an issue, right? That's the first issue. It's directly related to your answer already that has been given over there, which says that exact information requires to be defined for the decision boundaries. Again, I'll try to make that point in a slightly different way. This is the second thing that has been observed. That is, so you see, slight changes in your data points leads to this, right? So I had something like this, slightly it has been rotated, means though my data set remains same with slight modifications, we have some issues coming into picture, right? So I can say as a second point, the decision tree, uh, they are very sensitive. They are pretty sensitive uh, for very small variations. Okay, very small variations in the training data. That's the problem. Okay, now normally what happens, again, this comes into picture when we do the coding part. Normally the scikit-learn randomly selects which are the features to evaluate first at each of the node. So you see, you may get different decision trees for different runs of your same data. So that's what happens when we implement. We'll justify that as well. Okay, we'll show you that. So I run a tree, I run a model now, I create a model now, I get a different decision tree. For the same training data, I run the decision tree once again. You see, right? It will be a different one. Okay, so you know how to control this, right? You can set a parameter that is called as a random state, right? We have to use it. Okay, so every time I should get the uh, same samples, means I have to set a random state, right? So you can set that and you can overcome that issue. But again, uh, that's an that is an issue which comes into picture only when you do the training. All right, using the sklearn. Sklearn picks up randomly. That's the issue with the sklearn, but still it comes under the issues related to the decision tree. Okay, so uh, these are the issues. Anyway, the third one I'm not going to write. That's not a actually an issue with the decision tree. That's actually an issue with the sklearn implementation part. But anyway, we have a solution to overcome that right away. So we'll not consider that as a issue with that. So we could understand that random forests are pretty much efficient. So they are very straightforward.
Recording in progress.
So we know that the decision tree is pretty much straightforward. Okay, and the decision tree is also uh, very easy to understand. We have a lot of advantages over there. No parameters to be defined, etc. Okay, but still we have some of the issues, right, that we have seen just now. Okay, so the solution to this problem is to use a different different training algorithm, which uses the decision trees at some level, but in a different way. So they are called as the random forests. So issues with the decision tree leads to the next concept that is called as the random forest. Okay, so with that we have come to the end of today's session.